Okay, so let's start. Okay, so let's start. Good evening, everyone. I am Harshit Agrawal. Welcome to the fifth live session of mine for the week 5 of the course Structural Dynamics CE07. So, in today's session, we will cover following things. First, we will just review what was covered last week, that is in week 4 of this course. Then we will see what was taught in week 5, a brief review just to brush up the content and get everyone on the same level. Followed by a series of two questions, each one different from the other, based on the content covered in week 5 and assignment 5. I will first explain you the question and then step by step we will solve the question. So make sure you all have a pen and a paper besides you so that you can solve along with me. So in today's session, we will use MATLAB while solving the question also, along with some pen paper initial calculations. And in these questions, I have tried to cover as much content as possible, and going through them will provide you much clarity and confidence over the topic. Apart from this question, in addition to the MATLAB used in the previous two questions, that is question 1 and question 2, I will give another MATLAB question, and unsolved one this time, that you will need to solve on your own, and you will see the solution in next session. So just like the past live sessions of mine, I will step by step guide you how to code in MATLAB, and we will see the results. So if you have access to MATLAB, just keep it open in your laptop or PC. Else, just write the syntax along with me and try to replicate it later on. And if any doubts, can ask me in the next live session. So I hope everyone are clear with the instructions. If you have any doubts, you can raise hands or write your query in the chat box. I will respond as soon as I will see. So let's start. During the week 4 of the course Structural Dynamics, we learned about single degree of freedom systems with vibration induced due to arbitrary forces. So, what are arbitrary forces? These are some random forces or not non harmonic forces. So, according to the definition, these are structured under some random external dynamic force without or with some damping element present in the structure. We also learned about Fourier transformation and what it is. It helps to convert an ordinary differential equation into an algebraic equation, and thus helps us to visualize the response in time domain to be converted into frequency domain or vice versa as per convenience or need. In arbitrary force, we saw several special cases like constant applied, linearly increasing, and suddenly applied force in both damped and undamped system. The slide shows MATLAB response results of two of the situations we saw last week. The one on the left is the sudden applied force, where you see initially force is there in response, and after the force is removed, the structure is vibrating under initial natural vibration state post removal of force. And in the second figure, that is in the right figure, there is a constant arbitrary force on an damped system where response amplitude was observed to decrease with time. Now, last week, that is in week 5, we went on to learn about numerical methods. We went on to learn about numerical methods for solving single degree of freedom systems under vibration. If we go back to first week, we read that there are four ways to solve a single degree of freedom system, among which the last one was numerical method. So in this, we tend to iteratively see the response of a system over each small time interval in the total response period, and then try to get as close as possible to the actual response. Now, where this method prevails, when the force applied is a complex arbitrary force which we can't solve from any other method, or when the system is not linear anymore. So for non-linear system, there is only one method, which is numerical method. So the content of week 5 is divided into several modules. As in week 5 module 1, we read about basics of numerical methods, where it can be applied and what are its requirements. The major point of focus was selecting the appropriate time step. We'll see in one numerical today how it matters. In module 2, we learned about numerical method based on interpolation of excitation function, wherein function is broken into different small impulses and then net amplitude is determined. In module 3, we learned about numerical method based on central difference method, in which the previous and just after response is used to estimate all different responses. All different responses means displacement, velocity and acceleration at a particular time step. And in the final module, that is in module 4, numerical method based on variation in acceleration, also known as Newmark's method, we saw, which among all three is the most used one, wherein change in the response between two time step is estimated first and then used for calculating the response ahead. So moving ahead, we will just brush up all the formulas and relations we saw this week so that everyone can understand the numerical and MATLAB part coming ahead properly. So just to brush up the base of this course, the dynamic equilibrium equation is given by inertia force plus damping force plus stiffness force is equal to externally applied force. Assuming that the frame is rigid and deflection can happen only in the horizontal direction, a simple mass on a supporting column and the mass on the supporting column is also negligible. So a simple frame structure can be transformed into an analytical model as shown in the figure. So this is something we have been reading since week 1 of this course. Now, a SDF system, a single degree of freedom system, can be solved in 4 ways. In first week, we got an overview of this, but now we can understand all four. So what are these four methods? First is the classical method, in which the response of a structure is divided into two parts: the steady state response and transient response. So steady state response is due to natural vibration of the system, and transient response is due to applied force. Okay. And transient response is something which dies over time, and in the end only steady state response prevails, that we saw in classical methods. Then there was Dulleman's integral, in which applied force is distributed into small impulses, and the net response is the sum of responses due to these infinitely small impulses. Then we saw Fourier transformation, in which we convert an ordinary differential equation into an algebraic equation and see the response in frequency domain. And finally, we have numerical method, in which time step estimation of deformation based on previous deformation is done, and it is a kind of iteration method. And these methods prevails for structures, for system under arbitrary forces or when system is non-linear. Now, what are the requirements for a numerical method so that the solution obtained is close to the exact solution? There are three requirements: convergence, stability, and accuracy. So, a numerical method should converge to the exact solution if we decrease the time step. We will see how decreasing the time step affects the convergence later on. Stability. A numerical method solution should be stable in presence of any round of error. And third is accuracy. So we should get results as close to possible as exact solution. So these are the three basic requirements of numerical method. And based on these requirements, there are three methods to solve a single degree of freedom system using numerical method. First is based on interpolation of excitation function. Second is based on finite difference method of velocity and acceleration, and third is based on variation of acceleration, that is Newmark's method. Okay, so the first one is based on interpolation of excitation function. In this method, the applied force is approximated as a straight line in a small time interval. So considering a undamped single degree of freedom system, the total response then will be due to three parts: due to initial free vibration, due to the impulse created by the step force and due to the ramp force between two small time interval, as we are considering force as a straight line. So individually we can calculate the response due to three conditions. And so after estimating at and the total response at a particular time step will be the sum of all these three responses. And after estimating at a particular time step, the total response can be seen as a function of time just by recalculating initial condition and force applied before each time step. Second one is based on finite difference method of velocity and acceleration, and this can be done in three ways: backward difference, forward difference, and central difference. So in the course we followed the central difference method. So in central difference method, if the displacement at any time t is known, the velocity and acceleration response can be written as follows, that as you can see on the slide. And then substituting these responses in dynamic equilibrium equation, we can get a response function in an iterative way. Okay, we will see a numerical on this, like how to write the response function for central difference method using MATLAB. And at last, there is based on variation of acceleration known as Newmark's method. So there are some basic assumptions of Newmark's method. So using those equations, you there are some basic equations of Newmark's method and some assumptions for beta and gamma value. So using those equations and assumptions and the dynamic equilibrium equation, we learned how we can obtain change in response as a function of known and defined parameters. So finally, we saw how we can calculate the change in response as a function of time, and then using that change in response, how we can estimate the ahead responses. This also we will see through MATLAB in one of the numerical today. So I hope the week content is clear to everyone. uh, if so, we will proceed on with the questions now. Okay, so let's start with the question. So this is question one. What question says? Determine the dynamic response of a tower subjected to a blast loading. The idealization of the structure and the blast loading are shown in figure respectively. Assume damping equal to 20% of the critical damping. So here you can see a single degree of freedom structure under some induced vibration state, and we need to see the response of the structure, deformation versus time profile of the structure. So I will give you a couple of minutes to think about the questions and how we will proceed ahead and how to solve this question, and then I will proceed ahead. So we are on the first question of this week's course. You can read the question once, and in a couple of minutes, I will start with the solution. Okay, so let's see the solution now. Now, the what we have in the question, we know the structure whose weight is given and stiffness is given, and the blast loading applied on the structure. And we know that the damping is equal to 20% of the critical damping. So let's first determine the left system parameters. So first is the natural frequency. Now we know natural frequency is given by under root of k by m, where k is the stiffness and m is the mass of the system. But it is given weight of the system, so we need to convert weight into mass first. So it will be 100 into 9.8 upon 50. So it will be 4.43 radian per second. This is the natural frequency. Uh, Second is the natural period. So we know the frequency, the period will be 2 pi by omega. So it will come out to be 1.414417 seconds. Why we have calculated period here? Because we need to estimate the time step. And for time step, we will require the period. So according to the period, we'll set some time step and we'll see the response. Third is the damping factor. So we know critical damping is given by 2m omega n. So we know the value of mass and natural frequency. So the critical damping will come out to be 45.2 Newton second per meter. And since we know the damping coefficient, so damping factor will be critical damping into damping coefficient, that is 45.2 into zero point 0.2. So it will be 9.04 Newton second per meter. Okay, so how to now we'll solve this question by Newmark's method. Like Newmark's method will the numerical method that we will be using to solve this question is Newmark's method. So kindly open your MATLAB application if you have, or just write the syntax along with me. So we'll see how step by step we can define all the parameters that we need, and then how we can define a function which will help us to calculate the change in responses over time, and how using that change in responses will calculate the final response of the system. So step by step we will see how to write the main body of the code and the function, how to create the function. Okay, so this is my MATLAB command window. We need to create a new function in here. Okay, so let's start with the code. So the first thing that we always do while coding is to define the given values. So what are the given values? We know the mass of the system is 50 Newton, so 50 upon 9.8. Stiffness coefficient is 100 Newton per meter. Damping coefficient is 20%. So omega will be square root of k by m, and damping factor will be 2m omega n. 2m omega times damping factor. Okay. So these are the given values or the values that we can estimate from the given values. Now, second part will be to define time related parameters. So what are the time related parameters? We need to see in what range we need to see the deformation. So first at the delta t, like time step. Setting a time step value is very important when we talk about numerical methods. So let's go with the time step of t by 10. No, what is t? First we need to define the time period. So what is the time period of our system? 2 pi by omega. So let's set delta ts t by 10. Okay, and the total time frame will be 0 for each increment in time till, let's say, we will see the response till 5 seconds. Okay, so this is the time related parameter. So total we will have 36 points at which we will see the response. Okay, now we are talking about linear acceleration method. Okay, in acceleration method also there are two kinds: average acceleration method and linear acceleration method. So we'll go with linear acceleration method. What different comes in both the method? The value of gamma and beta. So for linear acceleration method, gamma is taken as 1 by 2 and beta value is taken as 1 by 6. This we saw in the weak content. Okay. Also, one more parameter that we need to define is the total length of the time step. So we'll define it by length of t. We'll see later on where we use these parameters. Okay. Now we have defined the given values. We have seen the time related parameters and we have defined the initial values for Newmark's method. Now we need to define the forcing function, because our forcing function is a kind of a ramp function where the value is initially increasing, then it remains constant, then it is decreasing, and then it is zero. So we need to define a function. This function we need to define first. Okay, so how we define forcing function f, and we will use a MATLAB command diff that will store change in f values. So we'll see how this diff command works. Okay, so how to define forcing function? Let's create a loop. So for I, any arbitrary variable I from 1 to tt, that's why we defined the tt parameter just above. If my time is less than or equal to zero point 0.05, so my forcing function will be given by, this is a linearly increasing line with the slope y is equal to mx, so m will be 120 upon 0.05. So f will be equal to 120 into t of I, the x-axis, divided by 0.05. This is when the time is less than or equal to 0.05 second. Now when the time is less than or equal to 10.1 second, so what will be the forcing value? Else if ti less than or equal to zero point 0.1, forcing function will be equal to 120 newton. So it is a constant value in this range. Okay, and then in the final part, when the okay, and then in the final part, the force is decreasing with time. So how we will define this equation using 2 point method. So this is one point where we know the forcing function value and the time value, and this is second point where we know the forcing function value and the time value. So how we write the equation? Y minus y1 is equal to y2 minus y1 upon x2 minus x1 whole into x minus x1. So like this, we know how to write a equation when 2 points are known. So less else fi will be maximum of either 0 or the equation 120 times time minus 0.15 divided by 0.05. So you can write this equation on your own and you will observe the same thing. Okay, so this is how we have defined the forcing function. So now we can end the loop. We have ended the if else clause and now we will end the for loop. So you can see the forcing function is again a 36 value matrix. So initially the value will be this, then constant, then this, and then 0 till 5 seconds. Okay. Now after this we need to calculate the difference in forcing function value. Why we need to calculate this? Because you can see here in the dynamic equilibrium equation we need delta pi for calculating the change in deformation. So how we can calculate change in forcing function value using the function diff of f. So I will define df1 as a parameter equal to diff of f. So between two consecutive points it calculates the difference. Okay, so you can see df1 is a 35 points parameter because when it will reach the 36 point there will be no additional 37 points, so it is a 35 point parameter. Okay, so now we will I hope this part of the code is clear. So after this we will define the initial conditions of the system. So what are the initial conditions? Initially we assume velocity is 0, displacement is 0, and velocity is also 0, and acceleration will be given by the dynamic equilibrium equation as f of 1 minus c times velocity minus a times displacement divided by mass. Okay, so this is how we will define the initial acceleration, and then we need to define the k bar value. What is k bar? Here you can see after such here we define the acceleration value and we need to calculate the k bar, which is a fixed quantity, and that we will use in the later on in the function for calculating the change in displacement. So what is k bar? K plus gamma upon beta delta t into multiplied by c plus gamma upon beta delta t squared multiplied by mass. So k bar is k plus gamma into c divided by beta delta t. We define delta or delta t plus m upon beta delta t times delta t. Let's recheck this equation once. And gamma into m. Okay, so this is how we define the k bar. Now when you need to define the these constant value also. So this is the first constant value and this is the second constant value. Okay, so let's name this as a and this is as b. So a is equal to m upon beta delta t plus gamma into c upon beta. M upon beta delta t plus gamma into c upon beta. Okay, and then b will be m divided by 2 beta plus delta t times c divided by zero point 0.5 times gamma divided by beta minus 1. Delta t into gamma upon 2 beta minus 1 into c delta t into c m upon 2. Okay, m upon 2 beta delta t. Here also there will be one delta t. Okay, so we have defined all the constant value. Now the next step is setting up for initial values of loop that will create. Okay, so u naught is equal to u, v naught is equal to v, a naught will be equal to a. These all value we calculated and t will be equal to first time. So first time is that is 0 only. Okay, so now we need to first define the Newmark's function. So originally defined it before also, but I will define it again for your understanding. So this is the function and we will define the function here. So function output, what we need output of display time, displacement, velocity and acceleration from the function is equal to, let's name the function as Newmark. So the input, all the inputs that we may need, t, a, b, tf, delta t, a bar, u naught, v naught, a naught, gamma and beta. So these are all the values that we saw here. These are all the values that we need for defining these change in displacement values. Okay, change in response values. So how we define the function? We first define df bar. You know na, here we saw delta p bar we need to define. So df bar is nothing but delta p plus a times p naught plus p times a naught. I will give a space here so that it is clear. Let's write as a df bar. So we know the df value and we know the k bar value. So du can be written as df bar divided by k bar. And then velocity can be written as, we saw the relation. I'm directly writing it now. Gamma u into delta u divided by beta delta t plus minus gamma into T naught divided by beta plus delta T times A naught multiplied by 1 minus 0.5 times gamma divided by beta. Okay, so this is d du dot value, and similarly du dot dot will be given by du divided by beta delta t times delta t minus v naught upon beta delta t minus a naught upon 2 times beta. So this is how we define all the relationships, these two relationships, delta ui dot and delta ui double dot. Okay, I have cross-checked the relationships, they are correct. Let's check here also if there is some mistake. No, you can proceed. So once we have estimated the change in displacement value, so head displacement will be given by u naught plus du. D is equal to v naught plus du dot, and a is equal to a naught plus du dot dot, and time is nothing but t plus delta t. So this is how we define the function. I hope this function definition is clear. We'll save this function as new mark. I have already saved, so it will just append that function. Okay, I need to close this function first, and now I can see. Okay, so this is how we define the function. Now we will see how to use this function. So the next part is iteration. So for I equal to 1 to pt minus 1. So till the second last step we will see df is nothing but df 1 of I. So at every time step, what is the difference in force that we have defined, and the response is t comma u comma v comma a is nothing but the function that we created, new mark. What all input parameter you need? T, A, T, df, k bar. We need to see, we need to make sure that the sequence is correct. Delta t, k bar, u naught, v naught, a naught, gamma, beta. So just cross check. TAB, DF, delta T, K bar, U naught, V naught, A naught, gamma, beta. Okay. So this is how we have defined called the function, and then we'll say the T response of is nothing but the T value that we are getting. Similarly, U response will be nothing but the U value that we are getting. V response will be nothing but the V value that we are getting. And A response is nothing but the A value that we are getting. So what we are, why we have written this part of the code, just to store the responses value in a final matrix so that we can plot them later on. Okay. Once this is stored, we need to append these values that will be feeded in again in the for loop. So U naught will be U this time, V naught will be V this time, A naught will become A, and T will be T only because it is appended actually. So now we can end the loop. If the code syntax is correct, there will be no error. So you can see there is no error, and you can see the response are stored here. A response, T response, V response, and U response. So once the response are stored, we can see the maximum values. So we can see maximum value. U max is nothing but max of U response. V max is nothing but max of V response. A max is nothing but max of A response. Okay, so on the side you can see U max, V max, and A max value and how they are varying. And then we can plot the response. So how to plot T response, comma U response, X label will be time in seconds, and Y label will be displacement in mm. Okay, so let's see the plot now. So you can see somewhere around we have miscalculated the displacement, but I can show you how the response should have looked like. So this is how the response will be. The displacement will increase with time, and then it will decrease, and it will increase and decrease, and this is how it will proceed. Now this is when we set the time period as t by 10 seconds. So if we are setting the time period to t by 20 seconds, we are decreasing the time step. So you can see the response function is little bit smoothing compared to a rough patch here. And if we decrease the time function further on, like this is t by 100, so you can see it is a completely smooth response, and it which is much closer to the actual response. You can see how the displacement is dying or off with time due to the presence of damping. Okay, so this is how we write response function using Newmark's method. Herein we may have miscalculated one of the values, so that's why the response came out to be a little absurd. But you can see this is how the response will look like. Yeah, we can rewrite. You can rewrite the code again, and you will see this response. Okay, I hope this question is clear to everyone. Okay, so now we'll move on with the second question. So I will give you a couple of minutes time to read this question and to think how we will do solve this question. Okay, so let's see this question now. So what this question says, it is based on the week 5 tutorial one. So what was that question? Idealize a multi-story building as a single degree of freedom system with equivalent mass and stiffness constant as shown in the figure. Assuming that the structure has 5% damping, determine the displacement time history of the structure subject to earthquake ground motion using central difference method. So in first question we saw Newmark's method. Now we'll see the central difference method, how to write the MATLAB code for it. So we know the weight of the system, mass of the system we know, stiffness constant we know, the ground acceleration we know. So first we'll determine the system parameters. So first parameter is natural frequency, that is given by under root of k by m. So k is 90 into 10 to the power 6 and mass is given 489.6 into 10 to the power 3. So natural frequency will come out to be 13.56 radian per second. Now second is natural period. So why we are calculating period? So this time we will set the delta t value directly as t by hundreds. We saw in the previous question that with t by 100 as the delta t, we were getting a very smooth curve and a much uh, closer solution to the exact solution. Okay, so delta t is 2 pi by omega n, so it will come out to be 0.46 seconds. And damping factor, for damping factor, we know the critical damping is given by 2m omega n, so it will come out to be 1.33 into 10 to the power 7 Newton second per meter. And then damping factor will be given by critical damping into damping coefficient. Damping coefficient is 5%, so it will come out to be 6.65 into 10 to the power 5 Newton seconds per meter. So this is how we have defined all the system parameters. Now we'll see the code, how to write the code for this. So I will first clear this screen and I will again create a new function here. So new function. Okay. So let's first write the main body of the code. So first again will be given values. So what all values are given to us? Mass is 489.6 into 10 to the power 3. Stiffness coefficient is 19 to 10 to the power 6. 19 to 10 to the power 6. Ground acceleration is nothing but 0.63 meter per second square, and damping coefficient is nothing but 0.05. So now we'll calculate the calculated value. We'll see how what values we can calculate from this. So omega is square root of k by m. Natural period is nothing but 2 pi by omega n. 2 pi divided by omega. C is nothing but, okay, it is 2 pi by omega. C is nothing but 2m omega times xi, and forcing function T naught is nothing but minus m times ug. We know how we came up to this function value. Okay, now we don't need to define forcing function here again and again because it is a constant function here. So we'll define the initial conditions now. So what are the initial conditions? Since it is not given in the question, let's assume initial displacement as 0, initial velocity as 0, and initial acceleration will be given from the dynamic equilibrium equation, nothing but P naught minus C times V1 minus K times U1 divided by mass. Okay, so these are the initial condition, and also we forgot we need to define time parameter. plus. So delta t will take n period by 100. So t will be 0 to delta t to 5 seconds. So for 5 10 seconds, you will observe the response. So you can see we will have a total of 1079 points. And length of this time period, what is the length of this time period? It will be 1079. But we need this value while creating loops, so we have defined. Okay. So now we will define the constant value that we need for estimating estimation of central difference method. So what are these values I'm talking about? These are these values. So in central difference method, this is the k bar which is constant, and p bar again is pi minus a times ui minus 1 minus b times ui. So this will be k bar, this will be a, this will be b, and u of minus 1. Initially u of minus 1 is also constant value that we saw in lecture, so that we will also define. So k bar will be given by m upon delta t square minus zero point 0.5 c upon delta t. A will be given by m divided by delta t square minus c upon 2 delta t. Okay. Here it was plus. So I will again define the k bar. Okay, and in A it is minus, and this is A. B is A minus 2 times m upon delta t square. Okay, and u minus 1, that initial value that we need is nothing but u1 minus delta t times v1 plus zero point 0.5 times delta t square times a1. Okay, so we have defined all the initial values that we need for estimation. Now, second last step is setting up initial values for loop. Just like what we did in previous question, the u naught will be u, v naught will be v, a naught will be a, and t will be nothing but t1. So first value is 0 only. Now we will iterate. So before iterating, we need to define the function. So how we define the function here? So again, the responsive that we need is p u v n a is equal to cdm. We will name the function as cdm, and the input parameter will be t a b t naught delta t t bar u naught and u minus 1. Just make sure you are defining all the parameters properly. Okay, so P bar will be given by, just like how we did in this last question, we need to define the P bar value. P bar is given by A of u minus 1 minus B times u naught. So this is how p bar is defined. U is nothing but p bar upon k bar. P is given by central difference method. So u minus u minus 1 upon 2 times delta t. So this is central difference method, and A is given by u minus 2 u naught minus plus u minus 1 upon delta t square. Okay, so this is the code. Now we'll save this code. So okay, so we have saved this function, and now we can call this function here. So we can call the function for I is equal to 1 to tt minus 1. Response will be t comma u comma v comma a is equal to cdm of t a b t naught delta t k bar u naught u minus 1. Just make sure that the order is same as what we defined earlier. This is k bar. Okay. Once we have defined the function, we'll get the responses values. So we need to store those values. T of I comma blah 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 will be t u response I comma will be u v response I comma this will be this a response I comma this will be. Okay, so we are storing the response so that we can plot the function later on, and now we need to append the initial values. U minus 1 will be nothing but u naught now. U naught will become u, so because u is ui plus 1, and t will be nothing but t plus delta t. Okay, so we can end the function. When calling the function, okay, here was an error we defined. Okay, now the function is proper. We again need to write this part of the code, but for now I'm skipping that. You can see later on how to write the response. Okay, so when this is done, again maximum values we can calculate as u max is equal to u response max of u response. Right now it is showing undefined because this loop was not completed. So in this way you can define maximum values and then you can plot the results. So when that plotting will be done, how will the result appear? So this is how we defined the function. This was the first part of the code, this was the second part of the code. Okay, so we need to define what mistake we did. There is one arrow mistake here that we did. So once we correct that, this will be how the response will look like. So you can see, due to damping, how the response is slowly decreasing with time. So this is how we obtain the response of a single degree of freedom system using numerical method based on central difference method. I hope this is clear to everyone. So in addition to this, we can also see based on interpolation of excitation function. So what you can do, just assume the initial displacement and velocity to be zero and there is no damping present. So once there is nothing such things present, what you can do, you can define one response by this equation, one response by this equation, and third response by this equation. After defining all three responses like we did in the two questions today, you can calculate response at a particular time, and for the next time period you can calculate the initial ui and vi conditions from based on the previous response and calculate the response for that time, and then you can plot the function. So this is something you can do on your own. In the next class I will show you the solution of this question. So this was all about today's session. If you have any doubts you can ask. I will be there in the meet till 8.